Hello, hello. Okay. Oh, you are live on the internet. Sorry about that. Let's take you off the internet. Okay, now it's on my whiteboard. All right, so we are going to play a little bit more with dot product, and then we'll jump into the cross product. So consider my writing utensils are missing. Come on. Hit. Come on. There you go. All right, so we're going to look at the dot product again. And one of the applications of the dot product was the projection of one vector on another. And I'm going to use the dot product and the projection to find a perpendicular distance. From a point to a line. So at the moment, we're doing more analytical geometry than calculus, but this is necessary because when you move on to vector calc, you're going to be expected to know quite a bit about how vectors work in the plane and in 3 dimensions. So first we'll do a 2-dimensional perpendicular thing, and then we'll do a 3-dimensional perpendicular thing. So I'm just going to pick a line. And the line I picked is, I think we played with this one the other day too, y equals 1/2 x plus 1. So let's get a little scale here and graph that sucker. So we have our y-intercept, up 1 over 2, we have a point over there, up 1 over 2, we have a point somewhere over there, and over here. So that's roughly our line there. I mentioned the other day that with lines and vectors, it's nice to write the line in standard form because then you can come up with what's called a normal vector to that line pretty easily. So let's put this line in standard form. To put it in standard form, we want integer coefficients, so we're going to multiply everything by 2. So I'm going to have a 2y. I'm going to have a 1x on the right. I'm going to subtract that over to the left, and then I'll have a plus 2, equals 2, excuse me. And typically we write it in alphabetical order, so we would write negative 1x plus 2y equals 2. Now, when we put it in standard form, that kind of switches the change in y and the change in x to go to the other variable. And so now we can turn this into a normal vector. Anybody remember what normal means? What's that? What? Say it again. Yeah, perpendicular. So yeah, or it's like orthogonal. So it's just kind of another word related to that. So normal vector would have to have the negative reciprocal of that slope, which these two numbers give us right there. So a normal vector here would be negative 1, 2. So starting at any point on the line, if I go 1 to the left and 2 up, I am perpendicular to the line in that direction. Okay, so then I'm going to pick a point outside of this line. So let's try the point 3, 5. So 3, 5, that's going to be somewhere around there-ish. And so what I want to find is I want to find that distance, the minimum distance to the line from 3, 5. Okay, so to do that, what I want to do next is just pick any point on the line. So I'm going to pick a nice easy point being the y-intercept of the line. So I got the point 0, 1. And then what I want to do is I want to create a new vector that's going to take me from my point here down to that point right there. Okay, so take a stab. What do you think that vector is going to be? What's that? Yeah, so we want to go 0, -3. So I'll have -3 for there. And then I'm going to do 1, -5, so then -4. Yeah, so we just subtract these two points or vectors. So again, just consider those vectors. I take that vector there, and I take that vector there. To get from endpoint of one vector to the other, we just do a subtraction. Okay. So this will take me from the point 3,5 to the point 0, 1. All right, so let's call that vector v. And I'm going to try and use the hat notation today. I practiced for like a half an hour before this, writing hats instead of arrows for you guys. Hope you appreciate it. But all my notes still have arrows. It's going to be interesting. All right, so the next thing we want to do is we want to take the projection of this vector onto our normal vector. Okay, and if we do that, it should give us this distance right there. So I'll take this to a new screen in a second. So we want the projection of our vector v that we just created onto our normal vector. And so our normal vector, again, because that's supposed to be a right angle right there, should give us that. So, anybody remember how to calculate a projection from the other day? So normally it would involve an angle, right? Cosine of that angle, that's one way to do it. Cosine of the angle along with magnitudes also gives us what? Dot product, okay? So if we don't know that angle, we can use the dot product instead. Okay? So what we want to do to get that projection, so projection of v onto n, is we want to find the dot product of v and n. And then we're going to have to divide that by the absolute value of n squared, so the magnitude of n squared. And then we multiply by that direction vector. Now we had a couple of different versions of this the other day. So this gives us the projection vector. Other versions of this were to take the magnitude of vector v times the cosine of the angle between the vectors times the unit normal vector, which should be that one right there. Now we don't currently know that angle, but this right here, remember, is the magnitude of the projection. So just a little review from last time. Remember, what is this guy over here? How do I characterize that piece? What happens when I divide a vector by its length? I get a unit vector. Yeah, so that's just the unit vector in the direction I want to go, right? So that's all that is. So unit vector in some direction. Oops, running out of room there. Okay, so if I compare these two right here, if I have the square of that normal on the bottom, if I just pull that back over here like that one right there, so rewriting one more time based on this version, if I consider v dotted with n, when I dot two vectors, do I get a scalar constant or do I get a new vector? I get a scalar constant, right? So this is just some number right there. If I divide that by the magnitude of n over here, I have left over n over the magnitude of n. So this right here is another way to consider the magnitude of the projection. And so if I'm just looking at the length of that perpendicular distance between the point and the line, it's the magnitude of the projection that I really care about. Okay. So to finish this problem off, all we have to do is take that arbitrary vector we kind of created, dot it with the normal vector, and divide by the length of the normal vector, and that should be the distance between those 2 points. Let's calculate that, see what happens. So we, oops, wrong way. So we have vector v is -3, -4. We have vector n, oops, line in the wrong spot, is -1, 2. So we need to dot those and take the magnitude. So our distance is going to be the dot product. So that's going to be 3 minus 8 divided by square root of 5. And what does that give me? -5 over the square root of 5. Now again, we're just considering the length of this, so we can take the absolute value of that. That cleans up nicely to be just square root of 5. Okay. So we can use the dot product to come up with perpendicular distance between a point and any line, okay, which is kind of nice. So exercise your geometric skills. I'm going to redraw that picture. Let's see, I also need what? Oops, wrong color. 1, 2, 3, 4, 5 is about there. 3 is about there. So we have the point 3, 5, and we have our line y equals 1/2 x plus 1. So reminder, how did I do this again? From here, I calculated the normal vector. To find the one easy way to find the normal vector is either to put it in standard form or just take the negative reciprocal of the slope, turn that into a vector. Then I pick some arbitrary vector off of that point to the line. Doesn't matter which point you pick. That's irrelevant, okay? Because then we're just going to project that back to the normal vector going over there. And then we just take the dot product of those two vectors, normal and some arbitrary vector from this point to the line. Okay, so besides that procedure, how else would you guys go about finding the perpendicular distance between the point and the line? This is a problem that could come up in a variety of contexts, different algebra, geometry contexts. So I'm just going to give you a second, play around, exercise your analytic geometry skills. How else would you find that perpendicular distance? Write something down. Don't tell me about it. Write something down. Yeah. Yes. So the bottom line is we're just concerned about the distance between the point and the line, so I just ignore the sign. Yeah. Okay, so try something. Don't be afraid to be wrong. Mathematics is mostly about being wrong first. Write something down, draw a picture, doodle. There's many ways to go about it. Some are more work than others.